So last time we started on the a tool we call the Z Transform. What we started is we are trying to solving for a linear difference equation. Linear difference equation describes a linear time invariant system. And we want to do is we want to find the output given the input and the system, which is defined by mathematical format like my signal is x in, my system is h in, it's the impulse response. And we have a formula which is convolution that relate the input with the system and give me output yn. So the difference equation is trying to solving for a current yn, and I want to express that in some closed format. So for any given n, I can immediately find out what is the output yn. Okay. Now difference equation, once I have all these constant coefficients a and b's, it can also help me to somehow to find the system if I know input and output, or find the input if I can observe an output and I know the system. However, we said if we are doing that, that means we are going to do a deconvolution. Mathematically, it's a little involved doing deconvolution. So we are trying to use some other mathematical tools to help us solve this problem, and we are using the Z transform. Okay. So today, let's get into that. A very useful math tool called Z transform. We're given the direct Z transform, which is transform a time domain signal into a Z domain signal. And then we have an inverse Z transform, which is a Z domain signal back to a time domain signal. Now, when we say transform, transform is an operator or operation work on a function. So I have x in, I do this transform. In our case, that is Z transform, that will also generate that another function, right? It's not just a value, it's a function. So we have a function we call it capital X, just give another capitalized character here. And then function, it should be a function of some variable. Now in that case, I just give that's a function of Z. The reason we are doing that because Z, according to our transformation formula, Z can be any complex number. So Z, this variable is complex. It's a complex number. Later, we will also see another very useful transform, which is called the Fourier transform. Fourier transform is x in that doing this, give it called F transform. F transform give me capital X as a function of frequency, F. Now it's also a function. It's a function of frequency. Frequency in this case is a real number, is a real variable. And some people like to use X omega. That's same thing. Omega is just radius. Omega equals to 2 pi f. Basically, they are the same thing. That's the frequency. Okay. So I want to just point out that transformation or transform is working with a function and generate another function. This is a special case of Z transform. Z transform, same thing. A function generate another function. Now this function is a function of a variable, and that variable is a complex variable, is Z. Okay, so doing the inverse Z transform, that's exactly the reverse. So we are having the capital X, trying to find the time domain signal, little x in. All right, so today we are also going to show some properties of Z transform. From signal systems, you have already learned another transform, which is the Laplace transform. Now, do you still remember the function expression for Laplace transform? If I have x t, right, this is continuous variable t, x as a function of continuous variable, and doing a Laplace transform. What do you get here? You will also have a function, capital X. What's the variable that you used? You're using a variable is s, right? Yes, it is XS. So S is a Laplace. It's a Laplace domain. That's also a variable in complex domain, right? This is a complex number as well. It's a complex number as well. So you see here, everything is similar. And now we have Xn. N is a time index, but it's discrete time. And then we got Xz. So these two Laplace transform and Z transform, they are very similar. They are almost all the properties are identical. The only difference is one with continuous time, one with discrete time signal. Okay. So if you still remember the formation for Laplace transform, and you can also extend it to here for the Z transform. So in the Laplace transform, probably you remember that it's an integration. So everything is continuous time, so it's integration. Now here, everything is in discrete time, so it's a summation on each time instance, right? The transform equation is given in the box. We have xz, that's a transformation domain function, xz, and it's an operation on the time domain signal. Time domain signal is xn. What we have here is xn times, it's a power series, times z to the power negative n. And then we sum together n from negative infinite to infinite. Okay, so we have here, z is a complex variable. Z is a complex variable. So I pick up every time domain sample multiplied by a power series z to the power, in this case, is -0, plus x1 times z to the power -1 plus x, here, x2 times z to the power -2, and so on and so forth. If it's a causal signal, I only have greater than or equal to 0 values. So it looks like that. It's a power series. And this can be expressed as an operation z working on function xn, or we simply using a connection. We're using a connection on top of that, we're putting z. It's a z pair. We call that a z transform pair, xn and xz. Now we need to understand that this described exactly the same signal. It's just one signal is we're looking at a function of time. The other signal we are looking in at the z domain or the complex domain, which is a function of z. So this is the transformation equation, but it is not complete yet. We also need to discuss the region of convergence, ROC. Region of convergence of xz definition is the set of all values of z for which xz attains a finite value. So I want to make sure that xz is finite. It's finite. Xz will not go to infinity, right? It will not go to infinity. It's finite. Now, why do we worry about that? Well, you have a power series. As we said, every time you put a power series, n is from, in general, it's from negative infinity to infinity. So you have x, let's put in a few terms here, z to the power 1, plus here is on the right-hand side of 0, and I have x -2, z to the power 2, and it goes on. And this is on the other side. So you have a z to the power of n, and you do this summation. It's by definition, it's infinitely large summation from negative infinity to infinity. If xn is a causal signal, you end from 0 to infinity. Still, it's an infinite sum. If you're adding something infinite sum, and the entire system will bust. It will blow up. You'll have the signal. It can be very large. You will not be able to define finite number of this signal xz. Okay. How can we guarantee that when I do the infinite sum, I still have a limited sum, so limited value of xz? We look at one example. Particular example is that if I'm just looking at this part, a causal part. Okay, if I am taking the z, let's say z is a value, but if I'm evaluate some xz, but according to this, if z is equal to 1/2, well, I may be safe. Let's give an example of all these x0 equals to x1 equals to x2. All these things are ones. So what I have here is power series sum. So this is z to the power -0, which is 0, z to the power -1 plus z to the power -2, okay? Now, since z is less than 1, and then I have a finite sum for this guy. That's a series of geometric summation, geometric series. What we have is the first term divided by 1 subtract this ratio, which is 1/2. Or theoretically speaking, it is first term 1 subtract the last term but the last term is very far away when n is very large, so it becomes 0. So it becomes that. So you get that. And that is a finite number. That is finite number. Now, for all z that is less than 1, I can always do that. So that gives me some of the hint for region of convergence. Convergence meaning that this guy, xz, is finite. Otherwise, it's diverged. It becomes infinitely large. So if I evaluate z equals to half, now in this case, if all the coefficients are 1, 1, 1, 1, I know if z is less than 1, I'm safe. So let me draw it here. This is my z plane, real part, imaginary part. Just for this particular example, if all the z's I can take, remember it's a function of z, right, are inside the unit circle, then I'm safe. All these valuated xz, this is kind of a 3D picture. So you can picture the value of xz is out of this picture. This is the plane picture just for the projection onto its z-axis. So it's onto the real and imaginary part. So everything within this region, xz is converged. It's finite. And we call this region as region of convergence. So we come to this region of convergence, we find out, well, it's really related with the idea of you have a power series, and I need to limit it. Make sure that x you evaluated is not infinitely large. So how to mathematically look at a region of convergence? Now I have z is a complex number. So I'm using a polar format. Z equals to its mole or amplitude times e to the power j theta, where theta is the phase. So r is equal to absolute value of z. Theta is the angle of z. So that's a polar form. We plug into the transformation equation. So xz equals to sum xn times this. Well, this is our original e to the power -n. And now it becomes, I have z equals to this, so I put into those two terms. In the region of convergence, that means xz is finite. So absolute value of xz should be less than infinity. Now, let me say that again. The region of convergence is that we're looking at this variable z. Where is the region? Well, this region is in the z plane, which is this is real part, imaginary part. And I want to find those z values in this plane, where it should be, such that if I evaluate, this is 3D kind of, if I evaluate this xz, this guy will be finite. And if this is satisfied, I said these are in the region of convergence. All these points that will form a region that is convergence. Okay, so let's look at plugging into my transformation equation. Xz absolute value equal to this absolute value on the right-hand side. It's a less than equal to, we put an absolute value inside the summation. So each individual terms, therefore I got a less than equal to. I got a less than equal to sign here. Not confused, let me just. And we look at inside the absolute value term. Now exponential e to the power -j theta omega. Well, I can put an absolute value here and here as well, right? So you put an absolute, and this guy goes away. It's 1. It's 1. It's always absolute value is always 1. So what's left is sum absolute value of xz times n r to the power negative n absolute value. Okay. Let me write it again here. Here, this term, we want to make sure it's finite. If it's in the region of convergence, that means this is finite. It's less than or equal to infinity. So xz is finite if the sequence, if this sequence is absolutely summable according to this formula. Okay. When will that be absolutely summable? Let's check with, so xz, we know it's already less than or equal to this, right? We'll get rid of the phase term, exponential term, so we're less than or equal to this. The summation variable n is from negative infinity to infinity. It's hard to discuss about the power series. So we divide that into 2 portions. One is I have this value, time value n, from negative infinity to negative 1. So everything here is negative term. So on the power term, you have negative sign here. So it's r to the positive value. It's a positive integer here. The second term is n from 0 to infinity. So we have xn, r to the power negative n. Okay. We change the variables. So basically we make n prime equals to n on the left side, on this side. So, excuse me, equal to negative n, and you plug in. So it's n prime, you just remove the prime, you give your variable n. So n from 1 to infinity, x negative n times r to the power n, absolute value. That's the first term. And then we have the second term here. So if I want to the first term finite, if I want to make this first term finite, now x is some number. It's a signal in time. So it's a finite number. It's just a weight, right? But this r is a power term. If I want to make sure this sum is finite, I need to make r small enough. I want to make this guy small. Now, whether or not it should be just bounded on 1, I don't know. Because in this case, I have xn or x negative n. It's not all ones. So maybe I have to discuss it. But the big direction is that because n, in this case, this n is positive number from 1 to infinity. So I want to make sure this r, the base r, is small enough in order for me to get a sum that is finite. The sum entire thing here, the first term is finite. Okay. The second term because r to the power negative n. So I put that into the denominator. It's also r to the n here on the denominator. If I want to make sure this sum is finite, then we need to have this r large enough. Now n is from 0 to infinity. N is a positive and a negative number. So if the base r is large enough, because it's on denominator, I can make sure it's a power series sum, and it gives me a hope this term will be finite. So big direction is on the first term is r is small enough, on the second term is r is large enough. Therefore, in general, the region of convergence should be bounded in this, between these 2 numbers. So this is the first one is determined by the first term. This is determined by the second term. R should be large enough. And combine these together, we find out the region of convergence is between R2 and R1. So in a complex plane, what does that mean? In a complex plane, that's the Z plane. Real part, imaginary part. So in general, the region of convergence grows like this. I have a circle with radius of R1, R2 here, the smaller one, R2 here. I have another circle here with the radius of R1. Okay, so the region of convergence in general, it looks like this. It's kind of a ring between these 2 circles, because I'm only checking with the absolute value. So those are the rings. Those are the rings, and that gives me this shaded region in general. It should look like this. Okay, so in general, it looks like this. This is the region of convergence. That's on the complex plane. We have the real of Z, imaginary of Z. And on the Z plane, the shaded region is the region of convergence. Now, you probably will argue that, now what about this R1 and R2 and R1? What happened? What happened if I have two numbers, but R2 is greater than R1? Is that possible? Well, that is possible because all you do is you use this on the left-hand side to generate or to pinpoint this number R1. And you use this side to find number R2. But these detailed number is determined by your samples, right? But determined by this. And I don't know, they are arbitrary. I can have any time domain signals coming in. So sometimes you will make R1 greater than R2, which is fine. Sometimes you will make it R1 smaller than R2. R1 smaller than R2. What will happen in this case? What do you think? Which is the absolute, the mole of Z should be within this range, R2 and R1, where this R is the absolute value of Z. So I'm only checking with absolute value. So that's a circle or circles. If I have that, but I find out I got a number, R2 is 3, R1 is 1. Well, the answer for that is the region of convergence is empty, right? You want me to find the region of convergence. If I got this value, what I'm conclude is that there's no way I can find any Z that give me a finite XZ. So the region of convergence is empty, it's an empty set. So similarly, we can deal with some other special cases. So in general, now if we have a caudal signal, a general case is that we do not have this term. Let me erase a little bit. If the signal is causal, I only have this term, right? If the signal causal, meaning that xn equal to 0 when n is less than 0. So this first term completely goes off. This term is 0. So I don't need to worry about R1. There's no R1 for me to worry about. Actually, R1 will be, in this case, it's infinitely large. So R1 will reduce to the infinite large point. In complex plane, that's also a point, infinitely large. So every point within is satisfying. If it's causal, and also the causals give me that I have no outer bound. Outer bound is infinite. And I also have here, let me don't forget that. I also have a finite duration signal. So this is signal, this is X. I only have those numbers. Out of this range, these are all zeros. And it's called these are all zeros. Therefore, I also don't need to worry about this term, right? I don't have an infinite here. It's a finite. In my previous example, it's 4 or 5 probably. And then you have finite sum adding together. It's okay. Not a big deal. R to the power of 5, that's largest. It's finite. So what we have here is that we got the entire plane except z equal to 0 because I do not want this r, which is right here on the denominator, to be 0. I don't want this. If r equal to 0, that will bust too. That will become very large, infinitely large number. So that's exactly this is the region of convergence. It's right here. Anti-causal finite duration signals. Anti-causal is that I have these part are 0 because it's anti-causal. It's finite duration, so beyond a certain value of n, beyond a negative number, it will be all zeros. And the region of convergence is the entire z plane except one point at infinity, z equal to infinite. So that's also giving me a region of convergence. If I have a two-sided finite duration signal, and then I have the entire z plane except 2 points, z equal to 0 and z equal to infinity. Okay. Now, in a more general case for infinite duration signal, then I really need to deal with infinite sum. Infinite duration, I have to deal with this infinite sum here. It depends on what direction you're going. I may also need to worry about the infinite here. I need to worry about infinite here. So when I have infinite duration, I need to really worry about this R because it's infinite sum. If it's a causal signal, so this is all 0. As we suggested before, if it's causal, that means you don't have outer bound. Outer bound is infinity. But because I have a infinite duration, right, this goes on. So I need to have, it should be greater than or equal to R2. Should be greater than or equal to, it's outside the exterior of a circle. This circle is given here, it's coming from here because I have this power term. I got this power term right here. And xn is on r to the power n is on the denominator side. So I need to have a r relatively large r. And relatively large r meaning that you need to define it's some exterior of something, exterior of a circle. So that's exactly what we have here. Now that's the region of convergence. Similarly, I got an anti-causal system. So I will have this region of convergence that's interior of a circle, which the circle is defined by R1. Two-sided and infinite duration. So it goes on forever. This goes on forever. Then I have the general form where it's a dish. It's bounded by R2 and R1. And another extreme example is what we just gave. If you calculate in this case that R1 and R2 should be has a larger number, R1 is a smaller number, then it just deforms into an empty set. For the Z transform, not only you need to give out this transformation equation. Let me use this original transformation equation. This is the first part, but you also need to second part is find the region of convergence. That completes the Z transform. If later on I ask you to do a Z transform, then you need to first do these two steps. A unilateral Z transform. Transformation equations look like this. It's a unilateral Z transform. So we are using that without saying that's a unilateral Z transform, but most likely we were talking about a causal signal. If xn is a causal signal, so even though you are doing n from negative infinity to infinite xn, c to the power negative n, but because it's causal, you don't really care about xn where n is less than 0. So I have that. We call that unilateral Z transform. And some literature, they're using the unilateral Z transform actually can help us doing the calculation for any of those causal systems and the causal signals. Okay, so now we know the Z transform, the direct Z transform. How to do an inverse Z transform? Inverse Z transform is, on the other hand, we have this function x of z. We want to find the original time domain signal xn. So that is the inverse Z transform. Well, it's a little involved because the variable z here, this z here is a complex number. This z is a complex number. N is a real number, so it's one. We have one excess. It's n is simple. Z is a complex number, and it's continuous. It's actually a continuous complex number, right? N is a time domain. It's just one dimension. It's discretized, so you can just sum. But Z is a complex domain. It's continuous. Therefore, I need to do an integration. But this integration is in the complex plane, right? In the complex plane, how are you going to find all these Z? When you do integration, you need to traverse your axis, in this case, my Z plane, and give me all these complex numbers. So the transformation equation looks like this. That's the inverse Z transform. The signal in time domain xn equals to 1 over 2 pi j, come to integration, xz, that's the Z domain function, times the power term, that's power term z to the positive n, subtract 1 dz. Okay. Now this contour C denotes the closed contour in the region of convergence of xz taken in a counterclockwise direction. So what does that mean? Well, first of all, I need to integrate over all these z's. I need to plug in all these z values, find xz. And these z's should all be in the region of convergence, because beyond that simply you don't have this term. It's an infinitely large number. You will not be able to put inside to do the integration. So the z we need to find, and we need to looking at those z's in the region of convergence. And it is taking a counterclockwise direction. So if I'm taking it at this point, what we do is we are going like this. And you check all those xz's according on this route, and it goes back to the your original starting point. Integrate all together, and that will find you xn. You don't have to do 2D. You don't have to check every point, as long as you can find a contour. So this contour is okay. You don't need to give me a perfect circle. Let's say I'm starting a contour starting from here, and you can go any direction. You may even come back and go whatever you like. But as long as in the region of convergence and it's counterclockwise and end it at your starting point, you do the integration. That's a contour integration, and that will give you exactly the same number of xn. That's what we have. And because the good thing is, because the region of convergence is a ring, right? We can always do that. We can always do this contour from the starting point to the end point, doing a counterclockwise and circling the origin and give back. So this is a transformation equation for inverse Z transform, and we don't really like that. It's complicated. I don't like to calculate a contour integration. Maybe you can program it. It should be easy, but it's calculated, just headache. So I'm just going to put it here, but later we will know in real calculations we seldom use an inverse Z transform using this contour integration. We were using some other technique. Okay, so now we have some time for the property of Z transform. So this Z transform is very simple, right? We have direct Z transform, inverse Z transform. We give out the equation. For the direct Z transform, you also need to define the region of convergence, and it's a function transform to another function transform back to another function. Okay. Given this mathematical tool, let's see what are the properties of Z transform. The first one is it's a linear transform. Z transform is a linear transform. So here is, if I have signal x1 and capital X1, they are a Z transform pair. I also have x2, capital X2, these are another Z transform pair. Then the combination of those two signals, linear combination, so alpha 1 times x1 plus alpha 2 times x2, where alpha 1 and alpha 2 are constants. They can be complex constants. And the linearity tells me that the Z transform of this guy, right, it will be also a linear combination of the output of the Z transform output of each individual signals. So I get x1z here, you give me capital X1z here, you have x2z here, you give me x2z here. And these are Z transforms, but by linearity, your combined signal is also a Z transform. So this and this they are also a Z transform. No, it's just Z transform. So linearity, as a matter of fact, you can extend it to many terms summed together. You don't necessarily limit it to 2, x1, and x2. You can have many terms. It's a linear operation. Time shifting, if xn and xz is a Z transform pair, then I have this. If I have a time shifting version of this signal, I'm looking at xn minus k, which is the sample at k period delay. Okay, so let's say if I have 1 time unit 1 delay, so I'm looking at k equal to 1, so xn minus 1. If I'm looking at 2 time unit delay, that's xn minus 2. Now remember, we have that, right? We have that before in our block diagram. We said I got a signal xn coming in, and the output is xn minus 1. We said this is a delay. What we did is we put this signal in a memory for 1 time unit, for 1 sample time unit, and then take it out. So xn becomes xn minus 1. We said that's a delay of 1 time unit. We're using a block diagram box, which is z to the power negative 1. Right, that is small case. That's a z to the power negative 1. Well, it comes from here because we have the time shift property. And then down the z domain, what we look at is we have xz times z to the power negative k. That's the time shifting here. It's showing at this point. So if I got xn minus 1, I want to find out what is z transform of this guy. Suppose I know xn and xz is a z transform pair. Then according to this time shifting property, we know that's z to the power negative 1 times xz, right? Because k equal to 1. That's the reason we have it here. We put a delay unit, we call it z to the power negative 1. It seems as if I have a signal coming in, multiplied by z to the power negative 1. Of course, that's in the z domain. And then we get in my delayed signal xn minus 1. The region of convergence of this signal is the same as that of xz, except for z equal to 0 if k greater than 0, and z equal to infinity if k less than 0. Okay. Now, how to prove this time shifting property and how to look at this, the region of convergence conditions, all we need to do is we're going back to the identity equation. This identity equation for Z transform, it's very easy. You plug in, you can prove that. And it's very easy. You can find out why the region of convergence will change a little bit because you moved the Z to the power negative K. So you need to care about if Z is equal to 0 or Z is equal to infinity. Otherwise, you have a power term here. You may have a danger when you got a 0 on denominator, it becomes infinitely large. It's out of the region of convergence. Scaling the Z domain. Scaling is that I have x and xz is a Z transform pair. Region of convergence is within this range R1 and R2. So scaling, I scale by this term is a to the power n. It's a power term. A to the power n times xn. Then on the Z domain, we will have this inside the parenthesis that capital X a to the power negative 1 to z. So that's basically, that's z over a. So it's a scaling. Scaling by a to the power n in Z domain, it becomes you kind of shrink by a. Region of convergence also changes. Region of convergence is if a is a positive number, it's a greater than 1 number. You expand it into a R1 and a R2. You expand this ring, but the inner circle, outer circle, they expand at the same time. To prove that, again, the same thing, we're using the definition equation of Z transform. We can prove this easily. Time reversal. This is a Z transform pair. We have a region of convergence. Then the time reversal, we're checking the signal from future to past, x negative n. Z transform, we got a x 1 over z in this format. It's time reversal. Time reversal in the Z domain, you are looking at an inverse. You're looking at the inverse of the variable 1 over z. And the region of convergence also becomes the inverse of my original region of convergence. So it becomes 1 over R2. Now R2 is a large number, right? So 1 over R2 is a small number. 1 over R2 less than absolute value of z, less than 1 over R1. Okay, it's still a circle, but all this region of convergence is taking the inverse in the Z transform. Differentiation in the Z domain. Differentiation in the Z domain, if I have xn and capital X, a Z transform pair, xn multiplied by a time index n, like time index, and I looking that into the Z transform, that as if I'm taking a differentiation of capital X, dx dz, It's a variable z, dx dz. And then I have another term here, which is a negative z here. So basically in here, we are changing this differentiation into a simple multiplication term, differentiation into multiplication. Now remember that ring a bell, right? You probably learned that in the Laplace transform. Laplace transform, everything is in the continuous domain. Therefore, you do have this integration and differentiation. In the Laplace transform, we also have that unit. We also have that property. You have in one domain, you got a differentiation. It's very difficult to calculate or to solve the equation. But you transform to the other domain, the differentiation becomes a product, becomes a multiplication. It will be easier to solve this problem. So same thing here, we got a differentiation in the Z domain. And then we have convolution of two sequence. This is more important. I have two signals, X1 and capital X1 is a Z transform pair. The second signal, X2, capital X2, it's a Z transform pair. The convolution of X1 and X2 in the time domain becomes a product in the Z domain. Right? So we have this convolution in the Z domain, XZ, the result, equal to X1 times X2 of Z. The region of convergence of XZ is at least the intersection of that of for X1Z and X2Z. Yeah, of course, that's the least condition I need to satisfy because you got two values here, and either one of them becomes infinitely large, then my system is infinitely large. So I need to follow at least the region of convergence of X1 and the region of convergence of X2, the intersection of these two. And there are some other special cases if you got those two multiplied together and you somehow change the region of convergence. And some other extreme cases we will see later on. You have those two parts multiplied together, but somehow they cancel each other. One is on the numerator, one is on the denominator. Somehow you cancel each other. So in a way, you extend your region of convergence. But we will see later on once we deal with real numbers in those signals. But right now, we just know that this is an important and a very useful property. That is, convolution becomes a multiplication. The same thing we used for Laplace transform, the same thing we will use for Fourier transform. Correlation of two sequence. Correlation is also a convolution. We know that just one signal is using a time inverse. It's correlation, convolution, the same format. Now, why convolution is so important? Again, we are dealing with a linear time invariant system, right? So describe a linear time invariant system, we use a convolution. Well, we use that a lot. So correlation, X1, X2, then the cross correlation of X1, X2, which is here. Now, this is almost very similar to the convolution. The only difference is that I have X1, and here I have X2. Instead of L minus N, that's convolution, I have N minus L. That's correlation, cross correlation. So according to this Z transform property, the Z transform of this cross correlation should be a multiplication of those two X1, X2. But because one of those is the time reversal. Now we just had that, right? Time reversal, it shows X2 is time inverse. It shows the inverse Z in the Z transform. Let me write a smaller Z, that's not a capital Z. Small Z here. Okay, so it's this term here. Therefore, indeed, we got that, and X1, Z times X2, a function of Z to the power -1. The region of convergence of R is at least the intersection of that of X1Z and X2Z to the power -1, 1 over Z. Okay. Last time, let me start using this as my last slides for today. Now, last time we were talking about this correlation. We particularly said that we have an autocorrelation, right? If I have autocorrelation X of L, that's the leg. We have this R, actually X1, XX of Z. Okay. What is this particular about this us? Do you still remember? We are doing a transformation on the autocorrelation of a signal. And last chapter, we give an example is actually we are not in the Z domain. It's a special case. Z domain is a more broad case. It's general case. But special case is I'm looking at the Rxx of omega of F. That's a frequency domain. Later on, we know. Later we will know that Z and omega, they are directly related by this. The same thing, e to the power j omega. Okay. What do we call about this? Do you still remember? We call that the spectrum of the signal. We are looking at the signal in the frequency domain, but we do not care about its phase. We only care about its amplitude. We call that a spectrum. And later we will see, indeed, spectrum is easy to calculate than the correlation, autocorrelation, because autocorrelation, you need to do this. Basically, it's convolution. But in the spectrum, what we did is, if you have multiple signal, it's a product. It's a product. It's very easy to calculate. Once you find this spectrum, you can do an inverse Z transform or inverse Fourier transform to find the autocorrelation signal, find the autocorrelation or cross correlation in this case. So these are the properties of Z transform, and I will stop here for today, and the next time we'll continue with more properties.